Okay, if not, I think we'll go on. I'm going to make the next presentation. It's entitled Multi-Scale Gravity Wave and Instability Dynamics. So I'm going to talk today about a single simulation that we've done, DNS, of a superposition of a very simple flow. It's a single gravity wave and a small-scale fine structure because the misalignments of the velocity fields in such a flow lead to the nonlinear interactions that drive the spectral evolution that is at the core of all of the nonlinear saturation theories. And I think it provides some very, very nice insights into the large and the small scale dynamics that accompany such a superposition, even under very idealized circumstances. So I want to acknowledge Ling Wang, who's here with us, who has done all the hard work with these simulations. And also, I'm also going to use a little bit of artwork from Colin and Edmund-De in this presentation. So as a background, in the late 70s, and in the early 80s, a lot of observations came to light, high-resolution stratospheric balloon soundings, for example, and MST radar measurements. And these all tended to suggest that when you looked at the vertical wave number spectrum of motions that were in the range of scales that we would attribute to gravity waves, there was a tendency for these to be confined or constrained to a spectral slope, as Colin mentioned earlier, of about -3 in vertical wave number at the high end, the high wave number end of this spectrum. And additional measurements in the troposphere, the stratosphere, and the mesosphere also suggested that not only was the spectrum constrained in shape, but it tended to be constrained in amplitude. So that begged a theoretical solution. Jerry Weinstock, as Colin mentioned, had an early theory for an m to the -3 tail. Other alternatives were offered. We suggested, for example, a number of colleagues and I, that linear saturation might constrain the amplitudes at high wave numbers, but it did not explain how the energy got to high wave numbers to begin with. Colin offered his Doppler spreading theory that he talked briefly about, and other theories came along as well. One of them that I thought captured some of the key physics, or a lot of the key physics, was the saturated cascade theory of De, where he basically took advantage of and relied upon the mutual actions of wave-wave interactions and instabilities to prescribe spectral shape and form. So there were lots of vigorous debates for approaching 20 or 30 years among these different participants, and some of them came to be characterized very nicely by various elephant cartoons. The one on the left, I think, nicely describes Colins' treatment of the initial nonlinear diffusion theory. The one on the right probably captures the view of the modelers who, subsequent to Colins' theory, questioned the applicability of some of his assumptions. My attitude was different. I felt that every theory relied upon assumptions, and the assumptions were different in each case. And those assumptions constrained the physics that you were able to embrace to see only a part of the bigger picture. And so it was the classic elephant and the blind man. And so this was sort of my representation of how we were viewing the field. And Colin was one of the blind participants in this, in my view. But not unexpectedly, Colin had his own view of the truth. And so he edited my cartoon. And this is him at upper left with his blindfold off, seeing the big picture, as he mentioned. Well, there's another member of our community who's not with us any longer, Edmund-De. He's always been a gentleman, and so his attitude was, well, let's try to be harmonious. And his alternative was a blend of wave-wave interactions and local instabilities. And his argument was that by merging those two processes, you could account for a lot of the individual spectra, the 1D spectra, that we see in frequency or wave number among the different wave components and the covariances. But the debate hasn't really changed, because since Colin and I stopped arguing about saturation theory 10 years ago, the questions are still the same. The observational and numerical evidence hasn't changed very much, but that's beginning to change. So the questions are still the same. Basically, what nonlinear interactions and instabilities control the spectrum and its evolution with altitude and time? What are the influences of background states? And are there things that we can learn uniquely from very high resolution numerical simulations because of the continuing advance in this computer horsepower? So by way of motivation, I think you can argue that wherever you look in the atmosphere, whether it's the stable boundary layer below 1,000 meters or whether it's at 100 kilometers, you see evidence of multi-scale superpositions. The upper plot here is from our McWave summer rocket program in 2002. 2003, but perhaps, and it basically shows very high resolution measurements, the red and blue lines here with our sodium LiDAR at Alamar. The black line is a coincident measurement, but not in the same volume, with the Cone instrument aboard a rocket by IAP. And each of these shows an interleaving of very highly stratified and very weakly stratified sheets and layers, and we see this structure at multiple scales, essentially from 10 meters in the atmosphere to 100 kilometers and above. We also see lots of evidence, also at various different scales, depending upon altitude, that look like evidence of local wave breaking or local shear instability. This is one very nice example from Frommer et al. With the very large Zenith telescope in British Columbia. It's used for guide star work. It's a 6-meter aperture, and so they have phenomenal photon collection capabilities, and they can look at structures in the sodium density with extraordinary resolution. And this shows a Kelvin-Helmholtz instability that's pretty clear, but it also is not static. It doesn't look like it's stationary. It seems to be modulated strongly in altitude by an underlying field, and that field must probably be due to gravity waves. So the figure at the right here is a movie. This is courtesy of Gerd Baumgarten, who has been photographing NLCs from the ground in Germany. This is looking over Oslo, Norway. It spans about 20 minutes, and I'm going to play it. And what you'll see in different parts of this field are local instabilities that occur, and they seem to occur at preferential sites within the large-scale gravity wave field, suggesting that there must be an interplay between the gravity waves at larger scales and the tendency or the lack of tendency at smaller scales for these instabilities. So good, it plays. So you'll see here, particularly at what appear to be kind of the capping structures in these waves, or particular phase structures, you see various instabilities occurring at various times, but the instabilities are not pervasive. They seem to be focused at specific regions in the large-scale flow. So we're going to attack this problem with a single DNS that's conceived to be very simple, and we're going to see how much of this large and small scale dynamics we seem to be able to find some evidence of. We have the luxury of structuring the computational domain to lie along the phase lines of the gravity wave. That's why it's tilted here. We choose a gravity wave with an amplitude of 0.5, so it has only 50% of the perturbation necessary to actually cause overturning, so it's basically stable for long times. And then we assume that we have a very small scale fine structure with a vertical wave number 5 times larger than that of the gravity wave, but that fine structure is horizontal, and the gravity wave is tilted. So we have to choose a domain which allows both of them to be periodic, and that's fairly straightforward to do. So this is a movie now of that flow shown in the vorticity field. The vorticity is saturated, so you can see the fine structures in the flow at later stages. It plays relatively rapidly. Initially, you'll see distortion of the phase structures. These blue lines are the minima in the vorticity, and they're really horizontal, so you're going to need to tilt your heads a little bit to the left. And I'll try to stop this at a couple of key points along the way. So you can quickly see the deformation of these two fields by each other because of their misalignment by only about 6 degrees. You can see initial overturning here. Up until this stage, this flow is entirely two-dimensional. Everything here is driven by the nonlinearities and the mutual interactions in the plane of the gravity wave itself. That quickly changes, though, and you see turbulence events now becoming very strong, localized, strong mixing here and here. You'll also see that the fluids in the upper and the lower portion of the domain are moving strongly from right to left, and the fluid in the middle is moving from left to right. This is a consequence of the superposition of the gravity wave and the fine structure. You'll also see evolving here in this region, moving to the left, what looks like sort of a plunging fluid or a fluid head, if you will. That we interpret as a sign of local, basically, gravity wave instability. It also begins to look at later stages a lot like a fluid intrusion, such as we often see in the boundary layer, where we can quantify these things very well. And another one is coming along here, and what is remarkable is in each case, the maximum tendency for turbulence, apart from the strong shear zones, seems to be when the fluid is moving strongly in the direction of gravity wave propagation, as if there is sort of a generalized gravity wave saturation criterion that would account for the tendency for instability because of the superposition of the large scale wave and the smaller scale structures. So there are a number of different instabilities that arise in this flow, At the earliest stages, because the gravity wave and the fine structure are misaligned, the fine structure acts on potential temperature gradients or potential temperature surfaces that are tilted nearly in the vertical, and so they cause very small regions where you have strong shear and also local convective instability. And that leads to instabilities that we have not yet identified in observations in the MLT, but I think are almost certainly there, and they're very akin to what we see as secondary instabilities in the outer portions of KH billows that have become nonlinear. They're very similar to the initial instabilities that we model when we look at individual gravity wave breaking, and they are very similar to what we also see in a sheared boundary layer that is convectively unstable. So those instabilities are well known, but we have not seen them yet, or at least recognized them as such in the MLT. The other instabilities that I showed with the movie are now highlighted here, this time not in the vorticity field, but in the energy dissipation rate field for kinetic energy. And I've highlighted here a couple. There's my cursor. The black ovals show the evolution in time. The times here span 2.5 buoyancy periods, or about 1/4 of a wave period. You see that this structure at t = 10 moves to the left, exits the domain here, re-enters here, and then evolves from this sort of initial local plunging structure to something that looks much more laminated and extended horizontally at later stages. And so that's what I would refer to as a local gravity wave breaking event or an intrusion. They really seem to sort of blend in their character in this multi-scale environment. The other instability that is very, very prevalent at later stages in this simulation is KH instability. You can see it at relatively small scales in some of the thin vortex sheets. You see it at relatively large scales here. And so these are the instabilities that we see most often in the atmosphere at lower and higher altitudes, and which also seem to be most prevalent in the numerics, which makes me think that even this very simple simulation is capturing some of the key aspects of these dynamics in the real atmosphere. So what does the simulation tell us about the interplay between wave-wave interactions and local instabilities? Because this has been the big debate between Colin and myself for a long time. The upper plot here, upper left column, shows the evolution of the primary wave amplitudes. The second panel shows the evolution of other 2D motions that are confined to that same plane. The third panel shows the evolution of the kinetic and potential energy of 3D motions, essentially instabilities and turbulence throughout. The time scale in all cases is in buoyancy periods. What is interesting is that instabilities do not occur until about t = 5, but all the action here in terms of the changes in the initial gravity wave amplitude happen at that early time before turbulence occurs at all. So turbulence can be playing no role in the decline of the initial gravity wave amplitude. Instead, that clearly is associated with resonant interactions within the box. You see that, again, the time scale and buoyancy periods here, and these are the amplitudes as a function of time of the gravest modes that arise because of the nonlinear interactions between the primary gravity wave and the fine structure itself, and then its various other components. Most of that all happens within the first 5 buoyancy periods. That's the time over which the kinetic energy in this other 2D field grows. And what happens when the turbulence finally turns on is that it acts strongly to suppress the other 2D motions. So we have a situation in which there are very clear, distinct dynamics. There are 2D dynamics that drive the spectral evolution, and there are 3D dynamics that limit those gravity waves in amplitude thereafter. So what does that imply for the spectrum? Well, this is the vertical wave number spectrum in the model. The horizontal remarkably looks the same, but we really don't have good observations of that, so that's more difficult to compare with theory. The initial spectra are shown here. Solid is 2D black, dashed is 2D, dashed is the 3D black. This basically is the initial noise spectrum in 3D. The initial 2D spectrum does in fact have a slope that coincides pretty well with -3 over almost a decade. But once the instabilities kick in, they constrain this, they remove that excess energy in the 2D spectrum, and they drive it to, again, roughly a -3 spectrum over the relevant scales, but now it is extended and it is more uniform, suggesting that the wave-wave interactions and the instabilities somehow act collusively together to create this overall spectrum. The turbulence spectrum is seen separately because that's now 3D. 3D black initially is way down here again before instability kicked in. This was the initial noise seed that allows the 3D structures to arise. The 3D spectrum at later stages after the instabilities have occurred is shown with the dashed red line, and we have a nice minus 5/3 slope here. So the model is able to reproduce a nice transition from a -3 gravity wave spectrum at larger scales to an inertial range minus 5/3 spectrum with a scale here corresponding to the buoyancy of the Osmodoff scale. So the model is beginning to capture some of the features we would like to see it capture in comparison with the atmosphere, but the range of scales that we can resolve so far is nowhere near what it is in the atmosphere. Some of the consequences of this are potential temperature structures. This is a time series at a 2 buoyancy period interval. At early stages, this mutual deformation of these 2 flow fields causes the fine structure to create many regions of local convective instability in very thin layers within the larger scale field. But as instability develops, you find instead that at each time you see a succession of interleaved sheet and layer structures that persists even to quite late times in these evolutions that are very reminiscent of what we see in the atmosphere. The lower plots here show the same evolution in the velocity profile in the direction of wave propagation, which is to the right here, and I've only highlighted with the arrows those regions where we see the maximum turbulence generation in the vorticity or the epsilon fields, and in each case they correspond to the most rapid velocity in the direction of gravity wave propagation. So again, that sort of generalization of gravity wave overturning seems to be able to explain a lot of what we see here. So I'll just list my conclusions and I'll answer any questions. Thanks. There it all.
If you go back to your plot, gravity wave amplitude as a function of, yeah, that one. So the gravity wave amplitude, are you using a normalized amplitude? So the maximum amplitude the gravity wave would have would be 1.
This is a non-dimensional amplitude.
Yeah.
So an amplitude of 1 would be when the gravity wave is incipiently convectively unstable. So this starts off at a stable amplitude, and it decreases by 30% and then stabilizes around this value here. So it loses half its kinetic energy very quickly, and it loses that energy entirely by wave-wave interactions. Instabilities at this stage have played no role.
So does this also mean that gravity wave nonlinear diffusion takes place, precedes the turbulence?
Well, whether you call it diffusion or wave-wave interactions or Doppler spreading, I think they're all kind of different words for the same interactions among the 2D wave field. Okay. And you know, it's necessarily constrained and in a small box here, and because it's in a small box, the spectrum that is allowed to interact is relatively discrete. What we really need to do is some of these same simulations in 2D or maybe 2.5D with limited span-wise resolution to capture instabilities in much larger domains so that we can see how well these same dynamics hold up on larger scales. Hanli?
Dave, I have a question. So if, say, at the same Reynolds number, if you perturb the wave field, but not with a wave, but maybe random motions, do you expect the evolution of the later turbulence or cascading to be similar or different?
Well, that's a very good question. What we need to do is simulations of this sort in 2D or, again, limited 3D that allow us to have a much broader spectrum resolving the gravity waves with different potential interaction components initially to see whether we ultimately the interactions flesh out and fill out the spectrum in the same way. That hasn't been done yet, but it's an obvious thing to try to do next. Or at all. Okay, last question, then we'll go on.
How does secondary gravity wave go into your simulations in terms of nonlinear interactions? So if you have nonlinear interactions within the primary gravity waves, then do you get a secondary gravity wave generation? And then would they be interacting with the primary gravity waves?
Well, the nice thing about a numerical simulation is if you're clever enough to figure out how to diagnose these things, all the information is there. We're not clever enough to do that one yet. The direct interactions are easier to quantify because we can look at the energy flow that accompanies specific products of wave numbers. But I would interpret your reference to secondary radiation to be the same as what Sharon and I would call it, and that is the consequence of local momentum deposition and wave breaking. And in that case, that can't really be as readily described by these larger scale structures. You'd have to say instead, what is the implication of that instability for the larger scale flow? How does that project onto the gravity waves separately?